So now this last example that we looked at before, we've worked out what the reaction forces are at A and B. And so now we can start thinking about drawing the shear force diagram, starting here, going up 11.8, and so on for all these different forces. We now know what to do about the UDL between this point and this point. And then we've got two more point forces, reaction force, and this at the end. So now you'll see what the effect of having the pivot is, or support rather, not at the end is. So just see where the reaction forces take you on this diagram. And I'll pause it while you have a go. So hopefully you ended up with something that looks a bit like this. If we compare it with the beam, we start with a reaction force of 11.8, which takes us to here. Nothing happens till we get to here, come down 8, which takes us to 3.8. Nothing happens until we start the UDL. So we're going to go down at the rate of 1.5 kilonewtons per meter until we get to 3.7, or minus 3.7 rather. So that's a point of maximum bending moment, because it's where it cuts the moment at the axis rather. And then nothing happens until we get to this point, so another 5 down. Nothing happens, and then another 12 down, which takes us to here. And then the reaction force of 40.7 cuts in, which takes us right up to here. And then we have the 20 kilonewton forces. So again, we should start and end at 0, and we do, hopefully. So just finish that shear force diagram if you haven't quite done it. So let me guide you now to drawing the bending moment diagram, and I'll leave you to have a go at it. If we look at this, remember, the area gives us the bending moment at a point. So again, I'm going to start at 0 down here and end, hopefully, at 0. So I know I can now work out what this area is to give me what the bending moment is at this point on the bending moment diagram. Problems start here though, look. Because I've got to have this area in this direction on the bending moment diagram because it's positive. But when I come to this part of this, that's going to be now negative. And to work out that area and that area, I need to know what that point is. And I don't know what that point is. It's an important point because it's a point of maximum bending moment. So I really want to know what that point is. And to work it out, I think about the idea of I can either think about the idea of similar triangles, because that triangle is similar to that triangle. So the ratio of that side to that side is the same as the ratio of that side to that side. So that means I can work out this side. Another way to think about it is to think in terms of this. It's coming down at the rate of 1.5 kilonewtons per meter. So it's starting at 3.8 meters and it's coming down at the rate of 1.5 kilonewtons per meter. At what point do we cut that axis? So either way, either the idea of similar triangles or to think about the gradient, you can work out what that point is. So that I'll leave you to do. Have a think about between yourselves. Once you've got that point, then it's pretty plain sailing. Then we want that area, that area, that area, and that area, and this area. And just see where the bending moment diagram takes you. It might go below the 0. It might go negative. Don't worry if it does, but you should end up at 0. Okay, I'll pause this and have a go. Right, let's have a quick look at this, and I'll just sort of go part way and discuss the points as we're going along. So we've worked out some areas. Whoops. So the first thing is, let's think about this area, because that will give us this point on the bending moment diagram here, the first point we get to. And what is that? I've got it here, so let me just check as you're going along. Does it come out to be 23.6? That's one I did earlier, just to get the values. And the gradient is a constant there in the shear force diagram. This gradient is constant, so the gradient is 11.8. Quite a steep positive gradient, which you can see if you draw the line between there and there. So that's the first bit. Now, two things we've got. The moment is going to still be increasing because that's this area here, but now the gradient is only 3.8. So we work out the next area, and that comes to 27.4, and that's gone up not so steeply. So that point there is 27.4. Gets a bit tight to get it all on here. And now we have a little bit of a problem because we want this area. What did this point come out to be, by the way? Have we got this far, and what do we get? 2.5. So in other words, do you mean 2.5 from here to here, or all to, so 5.5? Yeah, altogether. Yeah. Okay. So let's see a little side calculation. If we're doing this, well, let's do it by the 7 of triangles, because you might well have to do this yourself. So let's see. I know that's 3.8, and I want this. And I also know that that total distance there is 3.8, 6.8, 7.5. In other words, that this distance here is 7.5. And so I know 7.5 over 5, so I've got a little ratio. I can write down that 7.5 over 5 must equal 3.8 over x, where x is the distance I'm interested in, the similar triangles. The ratio of this side to this side, 3.8 to x, is the same as the ratio of this side, 7.5 over 5. So I might well have written the ratios the other way up actually to be more helpful, but remember from this morning I could just flip those two fractions. So x over 3.8 must equal 5 over 7.5. I want to get rid of that divide by 3.8, so times by 3.8, x turns out to be 5 over 7.5 times 3.8, which hopefully is 2.5. That's the sort of thing you do to work out where this point is, and it's an important point, so we need to be able to do that sort of calculation. It's important because it gives the point of maximum bending moment and also the point at which we start to go down, so negative moments. Once we've got that point, we can work out this area. And when I did this earlier, I think it took me to 32.2. So this point here is 32.2, according to my calculations. What am I going to draw between those 2 points? A curve, Jack, yeah. The gradient, if we look at this, the gradient starts off with a high positive value and ends up at 0. So it's going to end up horizontal. And so it starts with a high positive value and ends up at 0, at horizontal at 0. So it's a curve that peaks at that point. In other words, that's the point at which it levels off. And then I'm going to start to go down. So I work out that area. I'm trying to draw a curve here. Work out that area there, which will tell me what this point is. And again, the gradient is starting at 0 and going more and more negative, so it curves more and more like this. And I think that point is, can't read my own writing here. I want to say 13.63. So there are some values on there. See if you can confirm. It's not drawn very well actually. This should be a smoother curve around here and then go down and down. But I think you get the idea. Notice we have another point of maximum bending moments, the other point at which it cuts the x-axis up there. So we've got 2 points of maximum bending moment, one positive, one negative. And unsurprisingly, this one is at the support, which you'd expect in a way, wouldn't you? It's bending around that support. And that's the value of the bending moment at that point. Okay, continue the calculation, you should end up back at 0 there. So I'll pause while you do that. Okay, I think with that, you just maybe need to just take it slowly and check those values, you agree with those values. There are further examples in the tutorial booklet that you've got, and there are some solutions on the site where I go through some of the problems on calculating reaction forces, drawing shear force diagrams and bending moment diagrams. So have a look at some of those.